Okay, so, well, I would like to give my warmest welcome to Ms. Allison Barto, who is a director at Ball Aerospace, who will be presenting about exploring time and space, the future of space-based astronomical observatories. Allison Barto is a director at Ball Aerospace, specializing in developing complex space systems from vision to orbit. With over 2 decades supporting mission development for both NASA and defense customers, career highlights include 17 years in both technical and leadership roles for the James Webb Space Telescope at Ball Aerospace, where she led the team responsible for delivery of the optics and electronics for the 22-foot wide telescope, as well as for the overall optical design, verification, and orbit optical phasing and commissioning of the observatory. In 2017, Barto and her team were honored with the Aviation Week Program Excellence Award for Ball's work on the Webb's cryogenic electronic system. With experience building complex and audacious space assets, Allison continues to look to the future of space telescopes. She was part of NASA's recent In-Space Assembled Telescope study and is part of the follow-on SMART think tank on in-space servicing, manufacturing, and assembly. She served on a program panel for the National Academies Astro2020 decadal review process, which establishes national priorities for astrophysics space missions and ground facilities. And she serves on the Management Advisory Committee for the European Southern Observatory's Extremely Large Telescope project. Allison is an SPIE Fellow and recipient of the Women in Aerospace Achievement Award for technical contribution to the Webb Telescope program. And for obviously, my students have been made aware of the fact that the James Webb Telescope is one of the great achievements of human civilization. What I am surprised about is from the photograph that Allison can still smile after all that had to be done to get this thing up there. So I think that what the bio leaves out is her endurance, because I think that this project is not just a brilliant achievement of science and engineering, but also a testament to the resilience of all those who were committed to this project for so many years. So congratulations for success. And now we're going to listen to Ms. Barto's presentation. Please go ahead.
All right. Thank you, Fabrizio, for that excellent introduction. You know, although it took about 20 years from a formal program award through launch last December, those were very busy years, and we liked to say that we were working on the program was like running a marathon at a sprint pace the entire time. So it wasn't for the faint of heart, but was the type of just incredible opportunity to work on the cutting edge of what is humanly and scientifically possible, that I think all of us only dream of getting the opportunity to do at some point during our careers. I want to thank you for inviting me to talk with everyone today. And while we're about to talk about the largest and most complex scientific instrument that humanity has put into space, one of the things I really love about talking about JWST is it's a program where the engineering can be described to the lay person in a way that is just as exciting and accessible as the science, which is usually, of course, how we talk about these large astronomical observatories. And the process that we go through for engineering any system is similar, regardless of the size and the scale and the complexity, right? We still have to go through the same process. And so we'll talk a little bit about what we did to make that happen for Webb. And hopefully that will inspire you and let you think about how you approach other programs and projects that you might get to work on, whether as a student or in your future career. And even if they're not quite as large and complex as this, I think there's likely takeaways and ideas and tools from how we approached Webb that can be used to any type of project in the future. So with that, I'll start here. You can see a picture in the clean room at Northrop Grumman in Los Angeles, California, of Webb shortly before it was folded up and sent to the launch site. And I like to start with this picture because for all of us engineers, it really shows us that while we think about this beautiful, pristine thing in space, it is a human endeavor with a lot of equipment required. And this view from the clean room shows that. All right, so let's talk about space telescopes for a minute. When we ask people to think about a space telescope, the thing that generally comes to mind for everyone is the Hubble Space Telescope. And at the right, you can see some of the images that have been taken over the nearly 22 years of service that we've had from Hubble. And I always think it's worth taking a moment to reflect. You know, when our ancestors looked up at the sky and when they thought about space, they thought about the stars and the constellations and the nebula you can see with the naked eye through the Milky Way. And this filled them with awe. And we have always looked to understand our world better and our place in it by observation of the sky. Well, what's interesting now that we have the types of images you see on the right from Hubble is that these large space-based astronomical observatories that we're building today have really changed our cultural relationship with space. Today, if you ask somebody to think about space and the stars, they're likely to think about these types of images that we see on the right, and amazing structures and other galaxies. And it's fundamentally a different picture of space than generations before us have had. As I mentioned, Hubble has been the most scientifically useful spacecraft that we've had. It has the most publications and related to the science that it's done. And part of that is because of its longevity that was made possible due to servicing by astronauts. Why do we have this relationship though with the images we have from Hubble and not so much with the ones we have from ground-based telescopes? Why is it that we're putting telescopes in space at all? As you all know, putting anything in space is hard, right? It makes it a lot more challenging than just building something on Earth that you can go tinker with and fix and adjust at any time. The chart you see here looks at the atmospheric opacity. And in the bottom part of the chart, it's the same, but with numbers on the top as the bottom. Any place it's brown, the atmosphere is absorbing that wavelength of light. And then where you see the dips down towards the bottom of the picture, that's where light is able to make it all the way to the surface of Earth. So not surprisingly, you see the rainbow there, that's visible light. That makes it to our eyes. We're all able to see in the colors we know well. You can also see to the far right, there's a large deep trough. Those are radio waves also observable from the Earth's surface, which is handy for us for communications. But you can see that a lot of the electromagnetic spectrum is simply not able to penetrate our atmosphere and get to the ground. All of the gamma rays, X-rays, much of the ultraviolet on the left side of the plot, and the very long radio waves on the right are blocked. And similarly, in the middle, you can see many narrow bands in the near infrared that are able to get down to the Earth's surface, but those are just narrow bands. So much of both the near and the mid and far infrared are simply not able to penetrate to the surface of Earth. And when we recognized that, astronomers said, well, gosh, we're really curious. What is the universe telling us in these other wavelengths of light? We can observe what we can see, and it seems pretty interesting. What else could we discover? And so in the 70s, NASA embarked on what's called the Great Observatories program, where they set to create an observatory that would work in each of these major bands that are not observable from Earth, so that we could learn what we could from the universe at these other wavelengths. So there was the Compton Gamma Ray Explorer, Chandra, which observed in the X-rays, Spitzer, observed in the infrared, and then the telescope that we already talked about that everyone knows well, Hubble. It observed in the visible, but it also hit the UV and the near infrared. And so with these 4 great observatories that were designed to all be flying close to concurrently, we were able to observe phenomenon in the universe at all wavelengths of light. And there's a lot of interesting things we can learn if we observe these other wavelengths. And so fundamentally, that's one of the reasons we want to put telescopes in space. We simply cannot gather the information about our universe if all we're doing is looking in the in the visible from the surface of the Earth. Of course, there's other effects that are easier in space without having atmospheric absorption, and some of the challenges that creates. It's a lot easier to have a nice stable system and a nice stable image. Now, any good scientific instrument, we design them, right, to answer questions we might have. We might make a microscope to examine the very small, or a telescope to examine the very far away. Every instrument we create gives us more questions than answers. And these telescopes, and Hubble in particular, are no different. We put these up there. We've made amazing discoveries about our universe, how it works, how it was formed, how galaxies form from these instruments, but it still left us wondering more. And so around the time Hubble launched in 1990, we were already thinking about what are the questions that we don't think Hubble's going to be able to answer? What are the next questions we want to answer? And these questions that we came up with were really questions of origins. We wanted to understand how galaxies evolved over time. If you look back at the oldest galaxies, and I'll pause here, I don't know how familiar all of you are with the time machine nature of telescopes. This is one of the really exciting things about the field of astronomy, is we actually get to be time travelers as we explore space. Because light takes time to travel over any distance, the farther away the object is, the longer it's going to take that light to travel to you. And so when we look at very distant objects in the sky, that light has been traveling for a very long time to get to us. And one of the things Hubble is Webb is looking at doing is trying to see that very first generation of stars and galaxies that formed after the Big Bang. So if we look at the most distant objects in the sky that happened after reionization, once light was emitted, those most distant objects, the light has been traveling for the longest amount of time. So we're looking back in time to the very beginning infancy of our universe. So we want to understand, as we've watched through these observations we've made so far, we notice that the oldest galaxies are these kind of amorphous blobs, and the closest and therefore newest galaxies, like Andromeda or like our own Milky Way galaxy, have beautiful structures, beautiful spiral arms like the picture we saw on the earlier chart. And so we'd like to understand how that evolution happened. How did we end up with these structured galaxies we have today? We also want to understand better the origin of stars, the birth of stars, as well as the protoplanetary disks that form around them, understand how solar systems such as our own formed. And then moving on with this search of origins, if we're studying the protoplanetary disks and the formation of extrasolar planets, we would also like to be able to understand how common might life be on other planets, and start trying to definitively show if we are alone or not. And so these are a number of questions that we had as we started conceptualizing the next flagship class observatory that would come after Hubble. Eventually, after 6 years or so of early studies from the mid-1990s through about the year 2000, we settled on this design for the Webb Telescope. Now, when we look at this, it doesn't look like your typical telescope, right? You're used to someone looking through a big long tube. That's kind of what we all have in our heads when we think of a telescope. The Webb Telescope does not have a big barrel around it, so we get to see all its guts and insides, which makes it fun to talk about because you can see its structure a lot more than most instruments that we put into space, that by the time they're in space, they kind of look like big shiny boxes and might not be as obvious how they work. So first, let's just get oriented. Telescopes collect light and they focus that light onto cameras. That's fundamentally what they do. Most telescopes that we use today are the Newtonian style, which means we use mirrors to reflect the light rather than lenses to refract the light. Mirrors are easier to make, especially at large size. And by reflecting the light back and forth, we're able to shorten the overall length of a telescope. So you can imagine the old explorers from the 1600s and their long looking glasses that they would use. Those were refractive designs, and they were very large and long for a small aperture or width at the front. For telescopes using reflection, we are able to fold that light up on itself many times. So let's start by looking at what the light does on Webb, so we're all on the same page. The light comes in, it hits the first mirror, bounces off the second mirror that's out on those struts, and then goes into the center of the telescope, into that little black box that you see coming out of the middle. Inside of that black box, there are two more mirrors. There's a tertiary mirror, just the third mirror in the system. And then the fourth mirror it hits is a steering mirror that helps stabilize the image. And then after it hits that fourth mirror, the light goes into the array of several science cameras that we have on the backside. And whenever we try to build one of these large flagship type observatories, this involves a lot of people and is more than any one organization can do on their own. JWST is no different than that. And while it is a NASA mission, it is a mission of great collaboration. And there are contributions both from Europe, which contributed 1.5 of the science instruments, as well as the launch. It launched out of French Guiana on an Ariane 5, as well as the Canadian Space Agency, which supplied the Fine Guidance Center and one of the science instruments. The NASA portion, the rest of the observatory, was built by a combination of contractors and universities. The science cameras that were not provided by Europe or Canada were built in the United States. So that was 1.5 of the instruments. And then NASA owned how you put all of those instruments together and make sure that they're going to work as a system and properly be aligned to the telescope. Northrop Grumman out of Los Angeles was the prime contractor for the observatory. They built the spacecraft bus that you see at the bottom. They worked with key suppliers to build the large sun shield, which you see in kind of a dark gray. And then they had overall responsibility for the telescope. The telescope itself, the backplane was built by a company who does large composite structures in Utah, who has since been bought by Northrop Grumman. And then all of the optics that you see were built by Ball Aerospace, where I work in Boulder, Colorado. And we'll talk more about why the telescope looks the way it does and how it works, but I wanted to make sure we were all oriented as to what we're looking at here. All right, so when we think about Webb, there are two major factors of its design that are immediately noticeable. The first one is its size. Webb, as mentioned, has a 6.5 meter diameter primary mirror. Now, whenever we're building a scientific instrument, the thing we're building always comes from the requirements, right? Why is it that we're building what we're building, and why does it need to look this way? So we go back to those science themes that I talked about initially, these themes of origins. And the first one I talked about was wanting to see that first generation of stars and galaxies after the Big Bang and understand how galaxies have evolved over time. If we're going to look back at the most distant, most faint objects in the universe, that light has been traveling towards us for nearly 13.5 billion years. We are literally collecting photons, single photons from these distant sources. And just like if you leave a large bucket out in a rainstorm and you leave a small drinking glass out in a rainstorm and it rains an inch, they both have an inch of water in them, but the volume of water collected in the large bucket is much greater than the volume of water that you collect in the small drinking glass, just because of the diameter difference between the two. It works the same for telescopes. If we want to collect as many of these photons of light that are traveling towards our telescope as we can, the bigger the mirror, the more photons we can collect. So if we want to see these very faint, very distant objects, we need a very large mirror. Now, here is where the engineering comes in. Science is pretty straightforward. I want to see these distant things, so I need something big. But there's a problem with that, which is this telescope doesn't fit in any rockets. Now, we hopefully soon will have rockets available that could fit a telescope of this size, but certainly in the mid-90s when we began designing this, and even today, there are not existing usable rockets quite yet that could fit this telescope. So what did we do? We decided, no problem, we're engineers, we can fix this. We will simply fold it up. So Webb was folded with what we call, the telescope was folded with what we call two wings. Those are the three segments you can see facing you in the image on the left of the telescope stowed in the fairing. And then the large sun shield was folded up and stowed around the telescope, and the secondary mirror was stowed up above. In the video that you're watching, you can see the deployments that happened once we launched. And for anyone who's been following along with the progress of Webb since its launch on December 25th of last year, you probably noticed or saw the news releases as each of these steps of deployment were completed. All of the major structural deployments, the ones you're watching here, this large sun shield unfurling, unrolling, and then separating and tensioning, and then the booms coming down to hold the secondary mirror, and those two wings of the primary mirror coming out, all those happened within the first 3 weeks. And all happened very smoothly. This video used to be something that scared the public and the knowing aerospace community quite a lot. But we went through a very rigorous test program because we knew that we had to make it work. There's not a good way to fix and repair this telescope, so we needed to ensure that things would work correctly the first time. Okay, so as engineers, right, we knew we needed a big mirror, so we figured out how to fold it up, and then we figured out how to unfurl it once we got in space. So that's pretty good. We've solved most of the problems, but like any engineering problem, once you solve one problem, there's always another one, right? There's a repercussion of that. So the repercussion here, the challenge of what we've done with this mirror is that we've split it up into 18 little pieces, like you see, so that it could be folded up and fit in the rocket. Now, what happens during launch? Launch is a very violent event. This is a video of the Z-axis vibration test of a single one of those 18 mirror segments. Seeing the types of environments that it saw during launch. Now, of course, we had 18 of these mirror segments, and they were all doing this in all axes at the same time. When we launch, the mirrors are stowed to try to prevent them from shaking around too much, but there's still only 6.5 millimeters of space between adjacent segments. So that's a challenge because obviously we don't want them running into each other, but additionally, each of these mirror segments is just a piece of an overall mirror, and we need them to all work as one. So this is a simulation of the first image from JWST, and the actual first image is remarkably similar to this. Now, what we're looking at here is not several galaxies or nebula or stars spaced out within the field of view. What we're looking at are 18 blurry, out of focus images, one from each of the 18 primary mirror segments. Now, remember I said each of those segments needs to work together as one. But when we launch, all of these mirrors vibrate and shake, and so they all get misaligned. And so we needed to develop a way to take this image, 18 poor telescopes, and make them work as one. And that's the activity that's going on right now from our engineers at the Mission Operations Center in Baltimore, Maryland, at the Space Telescope Science Institute. We're working on pulling each of these images together into one well-focused image. Now, what do we do with the hardware to make that happen? In order to move those images around, we need to move the mirrors so that we can tip, tilt, and position them into alignment. On the left, you can see a close-up view of the actuators that are used to do that. On the right, you can see a technician working on the backside of one of the mirror segments. The actuator pairs that you see on the left are located kind of behind the triangular looking handling fixture that's the top most metal piece that you see in the picture on the right. So we have 6 actuators that work as a hexapod to let us control in 6 degrees of freedom the rigid body position of the mirror. And then if you look on the picture on the right, you see some thin little struts that extend from the corners of the mirror towards the center. And those are reaction struts that connect to a 7th actuator that's in the center of the mirror that lets us actually control the radius of curvature, so we can bend the mirror a little bit to get the curvature of each mirror segment just right. Now these actuators need to align the most precise mirror we've ever put in space. What does that mean? They had to have an individual step size on the actuators of around 7 to 10 nanometers. Now, I had a technician on Webb that liked to come over to my office at least once a month and remind me that a nanometer is an imaginary number. It's very, very small and not something we can see. So to put it in perspective, a sheet of paper is approximately 100 to 200,000 nanometers thick. And we needed to move in step sizes of 7 to 10 nanometers at a time in order to get the type of precision alignment we needed to meet our optical requirements. Okay, so we've walked through here briefly how to get from a really big mirror in space, right? We broke it up, we folded it, we figured out how to rebuild it in space to get everything aligned.
Allison, I just want to give you a heads up that we will have final guests at 12:10.
Yeah.
You're looking at the time? Yeah, okay.
Yep. All right. What are our other scientific needs? The next is, if you look at this telescope, it is a cryogenic telescope. And why is that? We built it to work in the infrared because we needed to see warm stellar birth. We said we wanted to see stars forming. And so if you look in the infrared instead of in the visible, you're able to see through the cold gas surrounding regions of stellar birth to the warm stars inside. Similarly, looking in the infrared lets us see very distant objects that have been redshifted. So we're able to see the signatures that used to be in the visible that have now been shifted into the infrared due to expansion over time. And similarly, if we want to look at the atmospheres of extrasolar planets and try to understand if they might hold some of the constituents required for life, for the same reasons that we can't see in the infrared in our own atmosphere, because our atmosphere absorbs those wavelengths, we need to observe those same wavelengths to look for those same absorption patterns in the atmospheres of other stars. So again, we want to look in the infrared. Now, in order to observe in the infrared with a telescope of this sensitivity, we actually have to cool the entire telescope. And if we cooled it actively using a cryogen or a cryocooler, it would be extremely hard because the telescope is so large. So this is why it has this open design, is we actually passively cool through two design choices. One is the orbit. So we've chosen to put this out at L2. That allows us to keep all the hot things in the sky, the sun, the Earth, and the moon on one side of the telescope. And as the Earth orbits around the sun, so does the telescope. And so we're always able to keep those things in a line. And then we built a large sun shield to essentially block all of that and act as a large parasol, if you will. Each of these layers rejects about 100 degrees and lets us go from having a warm, nearly room temperature spacecraft on the Earth observing side of that large sun shield to having a cryogenic telescope on the other side, passively cooled to about 30 Kelvin just by looking at deep space. Now, like any other engineering problem, we can keep it cool, but we have the problem that materials change shape as they go over temperature extremes. And so we needed to choose a material for the mirrors that would not change shape no matter exactly what temperature we cooled to. We have detailed thermal models, but you can imagine that there's always some uncertainty in that model. And we didn't want to be off by 5 Kelvin in our simulation and end up with a telescope that couldn't meet its requirements. So we chose to make the mirrors out of beryllium, which is a metal, very light, very stiff. And you go through a process of mining beryllium, creating a very pure powder, hipping it into a solid. Now, if we had just done that, the telescope would have weighed too much to get off the ground. So after that, we have to actually lightweight the telescope and hog out material. But again, because of the structural properties of beryllium, we were able to remove over 92% of the mass and still have segments that could hold their shape and survive launch. Now, the next problem is that when you cool it down, even though it performs well at temperature, it will still change shape. And so what you're looking at here in the bottom right is an interferogram that shows essentially the peaks and valleys of the mirror after it cools down. And we need to have a nice smooth mirror, not something that's ripply, if we want to have good performance. So what we then had to do is we had to take it down to temperature, see how it changed, and then polish the inverse of that into the mirror. So any place where it happened to bump up when it cooled down, we would polish a little divot into the mirror. And the next time it cooled down, it would cool down nice and perfectly. Again, these numbers here, 20 nanometers, don't really mean a lot. If one of these mirror segments was the size of North America, you wouldn't have a mountain or a valley larger than about 2.5 inches. So very, very smooth. But luckily the material is very pure, so it cools down repeatedly. I'll go through just 2 more charts in closing. I want to make sure that we talk just briefly about the new technology that needs to go into these sorts of instrumentations and the role of new technology in developing new spacecraft. People had the idea to put a telescope in space in the early days of the rocket age. And in the early 1940s, there was a concept to put an observatory in space. But the problem they had, if you look at this picture on the right, you'll see the little astronaut back there, is they weren't sure how they were going to keep the telescope stable enough when the astronaut that had to live in the back of the telescope would remove the glass plates from one image and put in a new glass plate to take another picture. And of course, at that time, all large telescopes on Earth, right, and a person had to ride along with the telescope and exchange those glass plates so that we could take pictures. And it wasn't until the advancement of CCD technology that let us have a digital means of recording images that we really had the technology necessary to plausibly build a telescope in space. For JWST, there were 10 new technologies that had to be developed. And this makes it very risky. In general, when we're developing programs for space, we want to have as few new technologies as possible, maybe 1, sometimes as much as 3, but 10 is pretty much unheard of. And some of the reason that it took so long to develop Webb was because we were doing everything for the first time and on a large scale. And just like we needed to develop these technologies to build Webb, when we think about the next generation of telescopes that we'll be building, we're going to need to develop other new technologies, which are all underway and beginning to be worked on now. So with that, we're at 2:11 my time, 12:11 your time. I will yield the floor. Thank you, Fabrizio.
Allison, I am truly honored that you made the time for us. Words cannot describe my pleasure in hearing you giving us this presentation, and what an amazing accomplishment, and what also an amazing accomplishment of a career, not just of a telescope. And the only question I would have, and unfortunately we have little time, is that we have young people here that would like to know how you have done all this from the standpoint of your career. I mean, what kind of self-administration? You know, for instance, we have physicists here who don't know that you are a physicist, from what I remember, but you now call yourself an engineer. So so do I, right? so what's going on would be the question, you know.
Sure.
Yeah.
Go ahead.
No, go ahead. You go ahead.
All right, I'll take a stab at that. I think that where we go in our careers and in our life are a combination of luck and of what you do to put yourself in situations to take advantage of opportunities when they come available. Yes, I am a physicist by training, by background, and as far as engineering is concerned, I'm a systems engineer. I would say I'm a systems engineer at heart and at my core. I like to understand how all the little pieces fit together and the connections between them, and how we can take advantage of understanding how things perform as a system to design the most efficient programs to do the most complex things. That being said, everything about engineering I learned on the job. I know a little bit about a whole lot of things, and that suits me very well. I think the thing to say is there's always more to do then you have people and time to do it. So as you're starting your careers, I recommend inviting yourself to meetings that you don't need to attend to learn. And while you're learning and listening, notice the things that might not be getting done because the people that are supposed to be working on them just don't have enough time. And if you have a little bit of extra time, which often when you're earlier in your career you do, find ways to help with those things. So that's my advice. Invite yourself where you're not necessarily needed, and look for opportunities where you could help people do their jobs, and take projects, help them with projects that they would like to see accomplished, but they don't have the bandwidth to finish and get to on their own, or ways you can help make what they're doing more efficient. And you'll find opportunities lining up for you. That's my best advice.
Well, ladies and gentlemen, Allison Barto, please come to Izmir, continue the conversation in person. So we would be delighted to discuss with you, to hear with you, the first year of observations next year. And as you can see down there, there are comments from physicists and engineers thanking you. Those are students who are very grateful. Allison, it was great that you found the time for us. I really appreciate it.
Absolutely. I'll also mention that nearly all of the system engineers that we had on the James Webb Space Telescope program, especially on the optical telescope side, nearly all of us were physics by training.
Okay.
I think physics teaches you how to solve problems when you don't have a lot of information. And when you're building things for the first time, that's pretty much what you're doing.
Well, I am delighted to hear it, and I would like to hear it again. Maybe I'm going to give you another call, and maybe one day you can address classes also, because I think that being midnight now here, I would like to have 1,000 people hear you speak. So thank you so much, Allison. I really appreciate
Absolutely.
it. Congratulations on putting it into the Lagrange point and for successful unfolding and deployment. And we look forward to the first data.
Excellent. Thank you.
Thank you, Allison.